Okay, I'm going to give you a little bit of dose of the industrial control systems world, or ICS world. This one is when data eats SCADA. My background is in the telecom sector for many years, and then in the electric sector for more years, and then most recently in the last 5 or 10, everything from mining, manufacturing, oil and gas, you name it. Let me grab the clicker. So operations, you'll hear a lot of things about operations. From my perspective, when I say operations, I mean actual utility or industrial operations. This is not like an IT shop, for example. We'll talk about some of the differences here in a minute. So what is SCADA? This is a typical HMI, human-machine interface. You use these all the time. You use them, for example, in an elevator. It's just buttons, right? You use them at a gas station when you're pumping your gas. You choose what you want. In this case, basically, this is a pumping system, and it tells you on the side where you can actually check things out, you can activate, and most things on here, believe it or not, are clickable. You can operate an environment by clicking on a screen. This is automation, and this is done so that you don't have to have people out in the field actually operating levers and switches and turning things and operating the machinery. You can do it from one screen. SCADA, Supervisory Control and Data Acquisition. That's what the acronym stands for. In a nutshell, whether it's power on a wire, water in a pipe, boxes on a belt, mining operations, and you name it. All it is, it's flow control. It's flow management, flow control. What's happening and how can I manage that environment? So you might have heard the term OT, you've definitely heard the term IT. OT is operational technologies, and obviously IT is information technologies. OT is the other side of the spectrum. It's that invisible industrial world that you probably have not seen. You might not even know that it exists, but it looks like these things here. These little devices are very small computers. In some cases, believe it or not, they operate back on the old x86 platforms. Some of them can be very old. I've even been in installations that are still operating today that run, for example, things like Conatel protocols on 300 baud, twisted pair copper. This stuff's been running for a very long time. It's designed to run for 20, 30, 40, 50 years or longer. It was built for reliability. It was not built for security. It was never designed to be connected to anything. So these little tiny purpose-built dumb computers, that's what they do. They literally sense something and report back what they're sensing, or maybe you can send a command to it and it will operate a lever or move something, open a valve, open a breaker. A lot of the equipment looks like this. It's mounted on a standard D-ring or D-rail for everything, and then you got your DB9 connectors. The modern stuff actually has Ethernet connections and USB connections, infrared connections. And this is like bleeding edge technology in the OT world. The IT space, you got a lot more horsepower than what they've got here. This is changing. Today, when you buy these products, you're buying OT that really is a hardened Linux kernel anymore. It's actually got decent processors in it. It's got a lot more horsepower, and some of this stuff even has things like web servers with Java, which we never really intended in the OT world to have anything like this. We don't necessarily need a 3D interface to a transformer for oil temperature, but for some reason that's what's being delivered in our platforms these days. So we joke about the fact that there's OT and there's IT, and as these things merge over time, it's really just becoming T. It's just technology. It's kind of all homogenizing and becoming the same stuff. And the form factor, regardless what you used to have lots of space to hold that much horsepower, we can put an enormous amount of horsepower in a phone, right? So that's getting smaller and smaller, and we'll talk about that. So what we're doing is we're replacing the old analog equipment with digital equipment. Analog equipment was great. It's what got the Industrial Revolution moving and got the industrial world in motion. The problem with analog technology is it's almost kind of brute force. It's difficult to sense the analog world and operate in the analog world with the degree of refinement and granularity that you can get with digital. I like to use, in a lot of cases, basically electromechanical relays in the power system. We used to have a lot more blackouts than we do, and that's because Basically, you're taking Mother Nature's most powerful force, you're trying to contain it and shove it down a wire and hope it doesn't burn everything in its path. We started with electromechanical relays. What they would do is they would say, okay, if the power goes outside of these boundaries, protect the system from burning to the ground. Those electromechanical relays are only so sensitive. With using digital technologies, we can actually predict, based on the speed of light, how the system is going to react based on power fluctuations miles and miles and kilometers away. It's that digital capability that gave us the power to do this. So using the analog equipment is fine, but in terms of really moving forward and actually getting full control and full efficiency of your system, digital is the only way. You can't buy analog solutions anymore. They just don't make them. They only make the digital stuff. So if you're a manufacturing facility, if you're a mine, if you're oil and gas or a chemical refinery, your choice is to buy digital stuff now. You just can't buy the analog anymore. Maybe on eBay. There's still some of it there. So we get all this equipment. It's got all this horsepower, all this technology built in, and then we connect it to everything. That's because it's digital. Why not connect it to everything? So we've got basically lots and lots of smart technology that is connected to lots of other smart technology, and it's gotten to the point to where everything in the plant is now connected to everything else in the plant. This was different even 15 years ago, 10 years ago, where you would have sensing equipment or operational equipment, and it would all come through what's called a remote telemetry unit, or an RTU, and this is like a refrigerator-sized cabinet. And it was all these wires coming in, and it would get aggregated and get sent out to some operational console, like that HMI I showed you early on. Now everything is all talking to each other, and all the devices are communicating back and forth, and you can basically get the health of everything all at once just by standard kind of IT-style communications. It's almost always over Ethernet. There's a lot more wireless technologies being introduced now because, frankly, if you need to run cables through a mine or a power plant or a water facility or some big industrial complex, wires are just a pain and it's costly, so you might as well just shoot some wireless around and it makes it a whole lot faster. So not only is everything connected, but it's usually connected wirelessly now. So infinite growth, and this one is an interesting concept. I call this logical distance. This is not geographic distance. Obviously, the concepts are different. Geographical distance is maybe I'm operating a piece of machinery 200 kilometers away from my screen. That's the geographic distance. The logical distance is all of the technology between the person clicking something and some physical kinetic action happening out in the field. If I click this, a valve opens. If I click this, a breaker opens. And that can be 100, 1,000 kilometers away. The logical distance is the mouse driver, the hardware abstraction layer, the network protocols, as it goes from Ethernet, MPLS, fiber, back through the other side, through some converter, RS-232, maybe into a Zigbee connection off to the wireless endpoint, into yet a different protocol for the industrial control side. We're shimming more and more and more and more technologies into this space between the click and the move that this logical distance is growing exponentially. And it's introducing surface area for attackers that we really haven't wrapped our heads around just yet. The challenge with the old technology and the new technology in the same space. As an industrial operation, you are required at this point, to operate the old equipment because it just works, and it will work, and it has worked for the last 20, 30 years. It's extremely expensive to replace, and typically you take your operation offline, which means downtime, loss of product, loss of money, to replace it. So you run it as long as you possibly can until you have to change it. And then typically you try to time these changes to change several things at once. May or may not work on time, you got to back things out, standard approaches for massive technology shifts. So in most cases, they're running these refrigerator-sized RTUs. At the same time, they're running all these brand new micro-sized widgets. And eventually, the technology was going to get so small that it'll just vanish out of sight. And if you don't believe me, we're already using things called smart dust. There's a great paper from MIT, some other technologies that are very similar. It's literally wireless, dust-sized sensor equipment for environmental conditions in plants. Requires no power, requires no connection, but you can get telemetry back from these particles basically. So the technology's already vanished out of sight. Think of it in terms of maintenance of different types of technologies. You get to manage the cutting-edge, dust-sized particle tech, as well as the ancient refrigerator-sized vacuum tube-style tech. That's a very difficult spectrum of technology to manage and maintain and secure. So as we replaced all the analog equipment that was painful to wire up, maintain and manage, get telemetry out of, as we replace it all with lots and lots of very inexpensive, tiny sensors everywhere that can communicate nonstop, now you basically have data endpoints everywhere that you never had data endpoints. Thousands and thousands and thousands of new data endpoints. So what happens when every single device in your operation starts generating a data stream? And you were never really wired for that. Where do you put all that data? There's no way you can hold it all. It's just impossible. Most manufacturing facilities don't have a data center to manage all the data coming in. Problem is, the operation, the business side wants that. They want the historical data. They want to see how machines are operating. They want to see how the humans are interacting with the machines. All of this is effectively money for the company. So what in a lot of cases is considered to be an air-gapped network, and I can tell you firsthand, I haven't seen an air-gapped network outside of a nuclear plant in less than probably 20 years. Air gaps are a lie. They're false. They just don't happen. And if someone says they're air-gapped, your first question should be, okay, so show me the firewall in the diagram. And they say, oh, well, it's right there. So that's not an air gap. It's a firewall. A true air gap means there is absolutely zero connection. The only connection is air. They don't exist. You're pumping an enormous amount of data out of the operational network, out of the OT network, into the IT network to get analyzed and used by the business. Now, what used to be that analog aggregated data out of the old equipment, now everything is sending data. What this looks like is the amount of data flowing through your firewall is huge. Where is it all going to go? The business side might have enough space in the business component to hold it all. Most manufacturing facilities are not, in your backyard. They're out in the middle of nowhere because no one wants some big stinky plant right next to their house. So you end up having to ship this data somewhere. Now the business has got to deal with all this operational data. This is a new problem for them. We haven't had this before. So what we end up with is people realize that data is money. So they innovated around this. And it's not just the utilities or the manufacturing facilities or the industrial complexes that realized this. It was third parties that said, hey, we can hold that data for you. We'll store it. We'll store it in the cloud. And then we will make data products out of that for you. It's a brand new operation, brand new third party, brand new businesses have sprung up overnight to do this for industrial operations. So the disruption to the industry has accelerated because now that sensitive operational data is no longer inside your boundary. It's shipped off to some third party somewhere being analyzed by who knows who, and then new data products are being created. This is the key, is that no one of these industrial complexes, these utilities, has thought about doing this until just now. So the challenge is, obviously someone else can do it faster, better, cheaper, because none of them really have business units designed to do this for them. So as these third parties come in, the challenge is, do you bring all of this in-house to try to keep this really sensitive information secure? I mean, most manufacturing processes are considered proprietary information, and industrial espionage is a very big thing. I mean, you think, auto manufacturers, defense manufacturers, even things like beverage companies. All of this stuff is incredibly important, sensitive information. Third parties are saying, we can do that for you, and you're having to kind of justify the challenge of, do you do this internally or do you do this externally? So effectively what happens is, what used to be, you were making widgets. You made a product. You refined oil. You pushed gas down a pipeline. You deliver water. Maybe you you generate electrons and you push them to some distribution facility. You're no longer in the business of making things. You're now a data company because you're generating so much data that the data products become a new revenue stream for you. So this changes the model. significantly because you're not just making stuff and moving stuff and selling stuff. You're now selling the data about the stuff that you just made, and that may actually make you more money in the long run. So the challenge with this new issue, as I mentioned in the previous talk, was that data is it's hazardous, it's toxic waste in a lot of ways. It's also an insane amount of money that you can make off of it. So it becomes both useful and toxic at the same time. So how do you manage, for example, your toxic waste that someone else is holding for you? What does that accountability look like? What does that third-party agreement look like? Or do you decide to do this all internally, yourself? These are basically the new challenges. We haven't really come to some resolution on this because we're still kind of wrapping our minds around in the industrial world what it looks like to go from basically pushing water, pushing gas, creating widgets, creating product, to selling the data about those things. Some of the interesting new ideas are, for example, we're just now starting to get into some of these areas. A lot of the equipment that we use is extremely expensive, millions of dollars for one component. I mean, think of a generation plant, like an electric generation plant. These turbines can be tens of millions of dollars for one turbine, and there may be 8 or 10 of them in one facility. The facility itself is a multi-million-dollar complex. The machines that are in there are very sensitive, so it costs a lot of money to maintain them. If I can take the operational data about how that turbine is behaving and sell it back to the manufacturer gets new data about real-time operational equipment. Usually all they get is failure mode. The device failed, fix it. Manufacturers are kind of left in that state of, well, we really don't know how to make it better other than this. So this gives a new data product just in that revenue stream alone. We're seeing some organizations like utilities, water, gas, electric, in particular looking at giving you free water, free gas, free electric if they can use your data and sell your data instead. Completely different revenue model for them. So we're at a stage now to where the data about the operations is actually more valuable and can possibly be a bigger revenue stream for the operational organizations than the actual product that they're making or moving. So what this does for those folks that are having to secure this is it creates new targets. I mean, traditionally it was always keep the proprietary information proprietary, don't let out the company secrets of how we do our manufacturing processes or our designs, our CAD drawings, whatever that might be. And now it's basically saying we have to protect all of that operational stuff and all of the new data components, data products. Not just in the traditional sense of, well, okay, is it gone to a third party? Do we still know who has control, or do we know who has access to it? But think about it in terms of what a data product looks like. If I can undermine the integrity of your data product, I don't have to steal it. If I can just change it a little bit, that effectively taints your product. Now your data products have to have full integrity from front to back. This is a different mindset. This is a different problem. Utilities, manufacturers, no one has thought about this yet. This is something that's brand new for us. So when we're thinking about how to secure these things, most of you may or may not be in the OT or ICS world, but this is coming your way, and there is a tsunami of OT operational push into the IT side of data warehousing and data management and data product management. And that's where this is going to, the solution to all of this is kind of this marriage of these two disciplines. And that's what I'm trying to get the message out, is we have to get OT and IT to talk together about some of these things. So in terms of protecting a manufacturing or operational technology environment, an industrial control systems environment, not only do you protect the process, which in industrial speak is how do you actually make what you're making or complete your process of manufacturing, chemical, mining, whatever it might be. It's always called basically process control. The product that you actually make or create or move, and then the data about it, because all of these things, because you don't get these highly valuable data products without those source components. And these are in two very different worlds in terms of technology management, and skill sets. So one of the first things people want to do is to regulate. And as a recovering regulator, I can tell you that may or may not be a good solution. So just as an example, I'm going to make a regulation. My regulation is when you ride your bike to work, you must lock your bike to the bike rack. This bike is compliant. think you get the point. Compliance does not equal security, and regulation is slow and hackers are fast. Technology will always move faster than laws in every single case. Trying to regulate your way out of some of these things is going to be very challenging. Market incentives may be better. Lightweight regulation that introduces market incentives at the same time might be better. But the point is that regulation will only go so far and will likely have unintended consequences. Every time I've been part of many regulatory discussions, was one of the original architects of the electric regulations in the US, the NERC CIP standards. Was at one of the biggest utilities there. We stood that up, and then I became the regulator to actually audit against it. And what we saw was you would set the bar basically such that everybody can participate. The regulation has to be written in a way that everybody in the entire industry can play. Well, as soon as we had that, there were organizations that were doing much more and organizations that were doing much less. Everybody normalized to that compliance bar, which was actually set very low so that everyone could meet it. After a while, they began to creep back up. But it's taken 20 years, to be honest, to actually come back up above that base level of just compliance. So regulation isn't necessarily going to solve the problem. What will, effectively, is, my message as always, is humans. Humans will change it. We have got to get a lot of IT folks versed in OT, and we have to get a lot of OT folks versed in IT, because eventually it's all just going to be T. The difference is going to be the data and where that data is sourced, to where it's housed, and how it's moved through that front to back initial process control all the way out to the data product side. So I would urge all of you, if you're not in the ICS world, spend a little more time. I mean, this may be your first kind of experience into the SCADA environments or industrial control environments. Maybe attend some more conferences and learn a little bit about the OT world. There are amazing and interesting protocols for those network nerds. Look up things like Profibus and Conatel and Modbus and DNP. These are some great protocols to learn. ICCP is an interesting one. It's a terrible bastardization of TCP/IP, but it still works, and it's how control centers talk back and forth. But there's some really interesting things in there, and the OT folks, talk to your IT folks. Understand what this is going to look like when you have to hand this data over so that they can protect it better once it's outside of your process world. This kind of conversation has to happen on both sides. So please go out, get cross-educated. This is going to help you, because honestly, critical infrastructure is one of the most important jobs you could possibly do. You're keeping the lights on, you're keeping the water flowing, you're keeping the gas moving, and it's, believe it or not, it may sound mundane, but it's quite satisfying at the end of the day to know that you're actually keeping society moving forward. So the point is, this can be done. It's new, it's innovative, it's highly disruptive. It's a very challenging situation that we're looking at, and we need some people to actually get ahead of this curve and be forward thinkers and solve some of these problems for us. And by all means, if you want to have any further chats about it, please come talk to me. I'm trying to get as many people as we can to at least start thinking about how we're going to manage this transformation that the industrial side is seeing, because it's new to us and it's very uncomfortable water. So innovate ahead of the disruption, get cross-educated, and I look forward to talking to all of you later about this. Thank you.
Thank you, Patrick. Now we have a little bit more time for questions. Some 5 or 10 minutes.
No.
I have a question. I mean, like, do I understand it correctly that basically we have connected the OT to IT, and now all the chemical and water plants can be operated from somebody's bedroom in either Riga or Tehran or Moscow or wherever your threat actor might be located?
Yes.
Well, it's...
The short answer is yes.
Yeah, and...
yeah, some of them use multi-factor authentication, some of them don't.
Yeah, well, I mean, we know how to bypass multi-factor authentication. You know, you first hack the provider of the multi-factor authentication service, and then
yes,
off it goes. So it's, well, how to sell this to the customer? Like, well, hi, you got like your water bill is like 5 cents less, but like, you know, the risk of you having no water at all is, you know, way
much higher. Yeah.
So.
Yeah, it was originally, this was done so that we could get the the data out of the operational networks because it was valuable to the organization. And then once they realized that, well, basically once the door was open, the door was open. Now there's a lot more connectivity going back and forth. There's not as much human interaction that crosses those boundaries. There are still some organizations that are one big flat network, and if you have access to the corporate side, you can still see the gas transmission system. Most of that is moving towards the isolation, where they at least isolate them. They're not air-gapped by any means, they're just firewalled off. But there's a lot more communication that's system to system. So many systems are communicating back and forth. So a lot of, in cases we see the exploits just happen from the system to system communications versus the human mechanisms. But yeah, take a look on Shodan. You'll see wind farms, manufacturing, chemical, water, you name it, they're all there. Yeah. So the short answer is yes, they are connecting them.
So thank you for your inspiring answer.
That's why we need more people to help design solutions for this.
So from my side, this is a very loud microphone, or just my voice is very loud. Maybe again, yes, no question. Now that SCADA or critical infrastructure industries, they are doing procurements, they are actually engaging in long-term marriage with the vendor.
Yes.
And whenever it kind of blocks the upgrade life cycle, you cannot upgrade unless the vendor actually ships it, because if you do it on your own, and everything breaks. I mean, the legal agreement might break. Is there a way on how to make this marriage work better in the future? Maybe not through legislation, or I'm not sure. Is there any solution?
Well, there is, at least in the US, there's a mandate to patch, for example, in the electric sector. And it's causing many systems to break because of that very reason. Whether it's, you know, ABB, Siemens, there's so many different management systems that manage your environment. There are the HMI, which is the human interface that you click in. There's a big rack of servers and databases that hold all the data that you're actually clicking, and it goes in there and then goes somewhere else out into the field. It's that other technology that's all Windows and Unix and Oracle and SQL, not those field devices. But it's that technology that they can't patch and they can't manage. If they do anything to it, the vendor basically voids their warranty and won't support them. And they have contracts for 10 to 15, 20 years in some cases. So I have seen systems that haven't been patched in 10 years. I've seen Windows XP. I saw a hydro facility running on DOS 2.2. Serious. So they can't patch. That's something that they, or in some cases, believe it or not, things will break. And the hard part is, it just sounds so simple, just patch the environment. Well, avoiding your warranty is only part of the problem. If you do patch the system and you actually cause the server or the HMI to react in such a way that actually harms the equipment, you may have caused millions of dollars of physical damage to a piece of equipment. So yeah, it's functionality as well. So it's not just don't patch because the vendor will void your warranty. That's just part of the problem. So I don't see an easy solution just yet until some of them are starting to think about more modularized software so that you can, and this is another piece I haven't even gotten into yet in a different talk, we're looking at virtualizing the entire manufacturing operation, plant operation, entire distribution system, virtualize the entire thing and then run an update and see how it affects everything. And have multiple virtualized instances so that you can actually test all the variances, and if you have issues, you can just drag a known good state onto a known bad state and start the plant back over. So it minimizes some of that downtime. They're beginning to think about the IT solutions there. The challenge is it's so complex, we're still trying to figure out how to get all that much complexity into a virtualized state and get realistic outcomes. Because even things like a hardware abstraction layer on a Dell box is different than a hardware abstraction layer on a HP box, and you may have differences in terms of driver updates. So it's not perfect yet.
We also have one question, at least from the online audience. That's probably an easy one. In Latvia, we practically don't have any manufacturing.
Right.
Do you think we're safe then?
Well, I see electrons being delivered to the lights in front of me, so you still have a power system. You still have a water system. I'm assuming you still have a gas transmission system. You've got to get gas to your pumps. You've got a transportation environment that delivers goods and products to your stores. All of these things have an industrial back end somewhere that you just forget about. You have no idea, absolutely unfathomable, how much work goes into you flipping a switch and the lights coming on. You have no idea how much technology is behind that and how much human horsepower is behind making that electron make the light come on. Beer manufacturing. Beer manufacturing. Come on. If that stops, it's a revolt.
Cyber beer. Okay,
Cyber-
thank you, Patrick.
Yes, thank you so much. Thank you.